This is section 2.3 for linear algebra, math 1114. Today we're going to learn about some special matrices, specifically the identity matrix and the zero matrix. We'll also talk about matrix powers and some non-properties. In other words, some ways that matrices differ from algebra. So the properties of matrices differ from properties of algebra. So for lack of a better topic, lack of a better title, we'll call it special matrices, powers, and non-properties. Okay, first of all, the definition of the identity matrix. The identity matrix is a square matrix, square meaning n by n. It has the same number of rows as columns, where the entries in the main diagonal are ones, and all of the other entries are zeros. The notation that we use for this is I sub n would denote the n by n identity matrix. So the subscript there, n, tells you the size of the identity matrix that you want. Let's look at some examples. I sub 2, as you see there, it's a 2 by 2 matrix. There are ones down the main diagonal and zeros everywhere else. I sub 3, a 3 by 3 matrix, ones down the main diagonal, zeros everywhere else. And of course, I sub 4 is going to be a 4 by 4 matrix with ones down the main diagonal and zeros everywhere else. The reason we learn about the identity matrix is because there's a very special property of the identity matrix. The identity matrix acts a lot like a 1 in multiplication. If A is an m by n matrix, then I sub m times A is equal to A. As you see there, I can multiply A by I sub m on the left side. I get back the same thing. It's just like multiplying a number by 1. Similarly, A times I sub n is equal to A as well. Here we have to use the subscript I sub n. We have to use the n because the dimensions have to match up with your multiplication. I'll show you some examples. Maybe this will become a little more clear. If we take A, which is 1, 2, 3 in the first row, 4, 5, 6 in the second, if I multiply I sub 2 times A, you notice the I sub 2 is on the left. I sub 2 is the 1, 0, 0, 1 matrix. If we were to multiply that out, as you see, I have a 2 by 2 times a 2 by 3. That's going to give me a 2 by 3. If you actually do the math, you really do get back the same thing you started with, 1, 2, 3, 4, 5, 6. Now that was on the left. I needed an I sub 2. On the right, I need an I sub 3. That's because A is a 2 by 3 matrix. The 3 has to match the 3 for the 3 by 3 matrix. And if you do the math there, you get, again, 1, 2, 3, 4, 5, 6. So here I had a 2 by 3 by a 3 by 3. That gives me a 2 by 3, which is the same thing again, A. Next we move to the zero matrix. The definition of the zero matrix is pretty simple, pretty predictable. Every entry in the zero matrix is a 0. You could have guessed that. It can be any size. It doesn't have to be square. The notation that we use, 0 sub mn, is the m by n zero matrix. In other words, it's the matrix with m rows and n columns, all filled with zeros. Let's look at some examples of these. 0 sub 2, 3 is going to be a 2 by 3 zero matrix. In other words, we have 2 rows, 3 columns, and everybody inside's a 0. 0 sub 3, 1 has 3 rows and 1 column. Again, everybody inside, all the entries are zeros. Now the reason we learn about zero matrices is because those two have some properties. If A is an m by n matrix, then If we add the same size 0 matrix to A, it does nothing to A. And again, you could have predicted this because if you add 0 to a number, you get back that same number. So similarly, if you add a 0 matrix, as long as the dimensions match up, you're going to get back the same thing you started with. Because there was a commutative property with addition, if I add 0 sub mn plus A, I still get A, or if I add A plus 0 sub mn, I get A. So the order there isn't important with addition. It is with multiplication, however. If I take my A matrix times 0 sub np, A again was an m by n, 0 sub np is an n by p, the inner dimensions match up. The size of the answer is still a 0 matrix, but it's 0 sub mp. So if I multiply by 0, I might not get the same size 0 matrix in the end. So you kind of have to watch those dimensions there. Similar situation if I take 0 sub pm by A was again an m by n. So I have a p by m by n. That's going to give me a p by n. So I multiplied by 0, a 0 matrix, but I didn't quite get the same size 0 matrix in the end. So just watch those dimensions. Here if we have an example where we have addition, so we have 1, 2, 3, 4 plus the 0 sub 2, 2 matrix, which is 0, 0, 0, 0, obviously that's going to do nothing to the original matrix. If I were to take the matrix consisting of 4 rows and 2 columns, first row 1, 2, second row 3, 4, third row 5, 6, and fourth row 7, 8, if I take that and multiply it by the 0 sub 2, 3 matrix, which is a 2 by 3 matrix, obviously we're going to get a 0 matrix in the end, but the 0 matrix we get in the end is actually a 4 by 3 matrix. So if I take the original, multiply by 0, I do get 0, but it's not the same size 0 that I multiplied by. Just be careful of the dimensions again. Next, let's look at what matrix powers would be. First of all, for a to the n power to be defined, A must be square. That's because if A were an m by n matrix, and I wanted to multiply by itself, the inner two dimensions would have to match up, and so I'd wind up with m having to equal n. So that would give me a square matrix. Now you're going to do these problems just as you would predict. If I take again the A matrix 1, 2, 3, 4, and I want to find A squared, I'm just going to multiply the 1, 2, 3, 4 by the 1, 2, 3, 4. Now as you see there, you remember you do rows by columns. So I took the first row of the first matrix 1, 2 by the first column of the second matrix 1, 3. And then I continued on with that pattern, row by column. And as you see, in the end, I get the matrix 7, 10 in the first row, 15, 22 in the second row. A lot of people seem to think that they can do some kind of a shortcut here and just take the original matrix and square all the terms. As you see, if I were to have done that, 1 squared is nowhere close to 7. 2 squared is not close to 10. 3 squared, 4 squared, none of those match up. So be very careful. Keep in mind you really do need to multiply these all the way out. What if we had asked you to find A to the third power? Well, A to the third power is just A squared times A. We had our A squared, which was 7, 10, 15, 22 from before, and our original A, which was 1, 2, 3, 4. And you can go to the trouble of multiplying that out, doing the addition. And as you see, you'll get some pretty large numbers there. You can find other powers as well. If you needed to find A to the fourth, you would take the result A to the third, multiply again by A. You can continue on like that all day if you want. Let's look at some non-properties now of matrices. There's a property in algebra that says if a times b is equal to 0, then either a is equal to 0 or b is equal to 0. That's how we used to solve a lot of quadratic equations. You might have something like x squared minus 4 is equal to 0. You would factor x squared minus 4, and then you would set the factors equal to 0, and that would tell you what x is equal to. Well, that was using this property. This property, though, doesn't apply to matrices. If capital A times capital B is equal to 0, if those two matrices multiply together to give you 0, it's quite possible that neither matrix is 0. Let's look at an example. Here I have the matrix with the first row 2, 2, second row 1, 1, and another matrix with the first row 1, negative 5, second row negative 1, 5. If I multiply out the first matrix times the second matrix, as you see, what's going to happen to every single term, I have, like in the first position, the 1, 1 position, 2 times 1 plus 2 times negative 1. Look at the 1, 2 position, which is first row, second column. I have 2 times negative 5 plus 2 times 5. Again, that's going to cancel out. As you see, every single position cancels out, and I do get the 0 matrix. Here, a times b is equal to 0, but neither a nor b is the 0 matrix. Another non-property. In algebra, if a times b is equal to a times c, then b is equal to c. We were allowed to cancel the a's or divide by the a's, which would essentially cancel them, and we were able to say b was equal to c. That doesn't work with matrices. We can't divide matrices. You'll find there are ways around this, but we can't divide matrices and we can't cancel matrices. Let's look at an example of this. If we take A, which is the matrix 3, negative 1 in the first row, 0, 0 in the second, B is the identity matrix, I sub 2, C is the matrix 1, 1 in the first row, 0, 4 in the second row. If I multiply out A times B, as you see there, I have a 2 by 2 matrix by a 2 by 2 matrix. And because that second 2 by 2 matrix is the identity matrix, I'm just going to get back the first thing that I started with, 3, negative 1, 0, 0. If I multiply out A times C, C was the matrix 1, 1, 0, 4, you'll find I still get the same thing, 3, negative 1, 0, 0. Well, here I've multiplied A by two totally different matrices, and I've gotten the same result. But are those two matrices equal? Is B equal to C? Absolutely not. So A times B is equal to A times C, but B is definitely not equal to C. Well, you've seen some special matrices. You've seen the identity matrix. You've seen the 0 matrix. You've also seen how to do matrix powers, which, again, was probably what you would have predicted. And you've also looked at some non-properties of algebra. As you've seen in the previous sections, the powers or the properties of addition with algebra do apply to matrices. So I can add and subtract matrices and nothing strange happens. It's just when I go to multiply by matrices that not all those properties of algebra hold. So what you'll need to do is go through some examples, go through some practice quizzes, and work on this for a little while. It'll become a little more clear the more you work on it.